Okay, so let's do this last problem here for this discussion. At highway speeds, a particular automobile is capable of an acceleration of about 1.6 meters per second squared. At this rate, how long does it take to accelerate from 80 kilometers per hour to 110 kilometers per hour? And as we're reading through this, we'll notice one thing that's a little bit uncomfortable. We have both meters per second squared and kilometers per hour as units, and so I'm probably going to need to change kilometers per hour to meters per second in order to make my problem work. And so I showed you a trick before, and I'll remind you now that most people in European countries and other countries outside of the United States that use the metric system know that in order to convert kilometers per hour to meters per second, they just simply need to divide by 3.6. They grow up knowing that, and it's part of their culture. Or to go from meters per second to kilometers per hour, they multiply by 3.6. So when I see a problem like this, I immediately just go ahead and write down or do that conversion right away so that I don't have to worry about it later on in the problem. So we're going to divide both of these by 3.6. If I do that, this turns out to be 22.2 meters per second, and this turns out to be 30.6 meters per second. Okay, so now I've got those values in meters per second, and I don't have to worry about converting them later on. So as I commonly tell you, I'm just going to say I don't know how to solve this problem, but I trust the strategy that I have to solve problems to lead me through it without having to know how to solve the problem to begin with. And we remember that our strategy is we start with a motion diagram. So I'm going to draw a motion diagram with my origin and the direction of positive x values. And then the second thing that we always do, is we just simply collect information. And remember, we always do this in a specific pattern. I collect my initial position first, final position, initial velocity, final velocity, acceleration, and then time. And this way, since I do this exactly the same way every time, I don't forget to collect certain information. And the information that the problem leaves out that you have to assume doesn't get lost. Okay, so for example, the problem doesn't tell you what your initial position is. It doesn't say your initial position is such and such. So when that happens, we're free to assume that our initial position is 0 meters. In this case, we're also not told what our final position is, so we'll come over here and say x is question mark. Then the next piece of information we collect is the initial velocity, and in this case, we were told the initial velocity is 22.2 meters per second, and I'll give that a velocity of a shorter length arrow there, because we'll want to make the arrows bigger as we go further, and my final velocity is 30.6 meters per second, and we'll make that a larger arrow, and we'll make our intermediate one intermediate sized. So we're accelerating, we're increasing the lengths of our velocity vectors, and we're doing this in the positive direction, right? The larger one is in the more positive direction than the shorter one, and so that means our acceleration also has to be in the positive direction. Okay, I use my velocity arrows to tell me what the direction of my acceleration is, and it's positive because we're speeding up in the positive direction, and I've been told that my acceleration is 1.6 meters per second squared. So just write this information down now. This is my given information. x0 equals 0 meters. I don't need to write down unknown information. My initial velocity is 22.2 meters per second. My final velocity is 30.6 meters per second. And my acceleration is 1.6 meters per second squared. Okay, and then I've been told that I need time. How long does it take for this acceleration to occur? Okay, so then I go and create a formula, and the only formula I know that has acceleration in it is acceleration equals the change of velocity over time, which is the same thing as my final velocity minus my initial velocity divided by t. That's the only acceleration formula I know, so that's the one that I have to use. And you might say, well, Marshall, how do I solve for time then? And you can either plug the values directly into this formula, or our practice is always going to become, we're going to isolate this variable and then we'll plug the values in. So if I want to get t by itself, I'm going to have to first multiply both sides of the equation by t, and that'll give me ta equals v minus v0, and then I'm going to divide both sides of the equation by a, and that's going to give me t equals v minus v0 over a. Now, the quicker you can learn how to do all of this in your head, the less steps you'll have to write out. Okay, but as long as you need to, certainly write out all of those intermediate steps. And then now we've got a formula we can just plug our values into. So I write out solve t equals, my final velocity was 30.6 meters per second. My initial velocity is 22.2 meters per second. And we're dividing by 1.6 meters per second squared. And this gives us a time of 14 seconds. Okay, and we don't really need, we don't really need this information anymore. Let's just get rid of that. And so this would be the solution that I want you to write down on your worksheet. Okay? So with that, I think that's the end of the lecture, but I go back to the video that we were doing. This is just a video clip that shows the solution to this problem. And that's it.